Okay, so picture this. You're leading a space mining operation, venturing out to tap into the wealth of resources hidden in asteroids.
Sounds like sci-fi, right?
It does, but it's closer than you think. And before you launch those rockets, you need to know where to aim. Luckily, you've shared some fascinating research on asteroid detection, a whole chapter from a book, in fact. So we're going deep on the tech that helps us find these cosmic treasure troves.
Yeah, it's not as simple as just pointing a telescope at the sky and saying, "Let's mine that one." We need to be precise. Detection technology is really crucial for pinpointing the most valuable asteroids,
Mm.
the ones that are just packed with resources that can fuel our, spacefaring ambitions.
Right, it's about quality, not just quantity. The book mentions that not all asteroids are created equal. Some are basically just space rocks, while others are loaded with platinum group metals. I know those are valuable here on Earth, but why are they so sought after for space mining?
That's a great question. What's fascinating here is how those metals translate to space applications. Platinum group metals are incredibly durable, which is perfect for, electronics that have to withstand the harsh conditions of space. They're also essential for creating efficient catalysts. And those could be used to process materials found on asteroids, creating a sort of self-sustaining system.
So it's not just about bringing the loot back to Earth, it's about utilizing it out there. This detection tech is the first step in establishing a real space-based economy. The book dives into different methods of detection, and one that always captures my attention is radar. I mean, we use it to catch speeders here on Earth, but how does it help us find asteroids millions of miles away?
Hmm. Well, it's the same principle. Just on a grander scale, we send out radio waves. And by analyzing the echoes that bounce back from the asteroid, we can determine its size, its shape, and even surface features. Some radar systems can even use different frequencies to give us a glimpse beneath the surface.
So it's like giving the asteroid a cosmic CT scan. We're not just seeing the outside, but getting a peek at its internal structure.
You got it. Different radar bands penetrate to different depths, revealing variations in density and composition. This helps us understand the asteroid's makeup without even landing on it. Facilities like the Goldstone Deep Space Communications Complex, with their massive radar dishes, are at the forefront of this technology.
It's amazing how we can use Earth-based systems to gather such detailed information about objects so far away. But radar gives us the structure. What about figuring out the composition? That's where the book mentions spectroscopy, which sounds kind of like analyzing fingerprints, right?
Precisely. Spectroscopy analyzes the light reflected from an asteroid. By setting the specific wavelengths that are absorbed, we can identify the minerals and metals that are present. It's like a cosmic signature revealing the asteroid's chemical makeup.
Okay, I'm following you so far. But the book mentions two types of spectroscopy, VNIR and TIR. Those acronyms are a bit intimidating. Can you break those down for me?
Of course. VNIR stands for Visible and Near-Infrared Spectroscopy. It analyzes how sunlight reflects off the asteroid's surface. By looking at which wavelengths are absorbed, we can tell if it's rich in silicates, metals, or even water ice.
Water ice. Now, that's something any space prospector would be thrilled to find. It's essential for life support and could even be broken down into fuel. That could be a game changer for long-duration missions.
Absolutely. Finding resources like water out in space opens up a whole new realm of possibilities for exploration and even colonization. Now, the second type, TIR, stands for Thermal Infrared Spectroscopy. This one's all about measuring the heat radiating from the asteroid.
So VNIR is looking at the light reflecting off the surface, and TIR is measuring the heat coming from within. It's like we're getting both a visual and a thermal fingerprint.
That's a great analogy. And those thermal readings can tell us a lot about the asteroid's composition. A metallic asteroid will radiate heat differently than a rocky one, or one that's rich in icy compounds. By analyzing these thermal signatures, we can make educated guesses about what lies beneath the surface.
This is all incredibly detailed information. And we're getting it from millions of miles away. It makes those stunning images we sometimes see of asteroids seem almost like snapshots from a family vacation. But the book also talks about optical imaging as a key technology. What role does taking pictures play in all of this?
Well, while radar and spectroscopy give us a lot of data, optical imaging provides that visual context. We use telescopes on Earth and cameras on spacecraft to capture images of asteroids. These images help us create 3D models, map surface features, and even scout potential landing sites for future missions. They give us a real sense of the asteroid's terrain.
So we're combining the scientific data with visual confirmation that space is vast and those asteroids are relatively small. I imagine getting clear images must be quite a challenge.
Yeah, you're right. There are, quite a few hurdles to overcome. Distance is a major factor. The further away an asteroid is, the smaller it appears, requiring more powerful telescopes or closer-range spacecraft to capture those detailed images. And then there's the issue of light scattering. The way light bounces off the asteroid's surface can obscure details, making image analysis a bit tricky.
So it's not as simple as snapping a quick pic. We're dealing with cosmic shadows and reflections that complicate things.
Yeah, exactly. That's why it's so crucial to integrate all three technologies: radar, spectroscopy, and optical imaging. Each provides a different piece of the puzzle, helping us build a complete and accurate picture of the asteroid.
It's like the old saying, two heads are better than one, but in this case, it's more like three technologies are better than one. By combining these different perspectives, we're minimizing uncertainties and getting a much clearer picture of what we're dealing with.
Precisely. And that comprehensive understanding is essential for planning safe and successful mining missions. We need to know the size, composition, and orbit of the asteroid to extract resources effectively and avoid any unforeseen hazards.
This focus on safety and precision makes sense. We're not just talking about grabbing a chunk of rock. It's a complex operation that requires careful planning and execution. And speaking of planning, the book also touches on some really exciting future technologies for asteroid detection. Things like AI, swarms of small satellites, even the use of quantum technologies. It feels like we're on the cusp of a whole new era of asteroid exploration.
Yeah, you're absolutely right. These emerging technologies hold incredible potential to, revolutionize the field. AI, for example, can analyze vast data sets from telescopes and space missions, identifying patterns and trends that would be impossible for humans to process on their own. It's like having a supercomputer sifting through mountains of data, helping us pinpoint the most promising asteroids for further investigation.
So it's like having a digital prospector, constantly scanning the skies and alerting us to potential gold mines, so to speak.
That's a great way to put it. And as AI algorithms become more sophisticated, they can even predict the properties of newly discovered asteroids based on their spectral signatures or radar reflections. We're essentially building a cosmic database, cataloging asteroids and their valuable resources.
That's incredible. It's like having a crystal ball that tells us what an asteroid is made of before we even get close to it. But AI is all about the data analysis. What about actually getting out there and observing these asteroids up close? That's where the idea of small satellite swarms comes in, right?
Exactly. Instead of relying on a few large and expensive spacecraft, we can send out constellations of small, low-cost satellites to continuously monitor asteroids. It's a more agile and cost-effective approach.
So instead of one big observatory, we're talking about a fleet of tiny scouts constantly reporting back on what they see.
Precisely. These swarms can provide high-resolution imaging and spectroscopy data, giving us a much more comprehensive and dynamic view of the asteroid belt. And because they're smaller and cheaper to build, we can afford to send out more of them, increasing our coverage and reducing the risk of losing data if one satellite fails.
That's brilliant. Safety in numbers, even in space. But it doesn't stop there. The book also mentioned the potential of quantum technologies in asteroid detection. Now, this sounds like something straight out of science fiction. Can you shed some light on what that might entail?
Sure, quantum technologies are still in their early stages, but they hold incredible promise for revolutionizing many fields, including asteroid detection. One particularly exciting application is quantum imaging. Imagine being able to resolve surface features on an asteroid that are currently too small or faint to be seen with conventional telescopes.
Wow, so we're talking about seeing things that are currently invisible to us. It's like having a cosmic microscope.
Exactly. Quantum imaging could unlock a whole new level of understanding about the composition, structure, and even the history of asteroids. And quantum spectroscopy could allow us to detect and analyze light with unprecedented precision, revealing the presence of rare elements or even complex organic molecules.
It's like having a cosmic fingerprint scanner that can detect even the faintest traces of elements and compounds. These quantum technologies sound like they could rewrite the book on asteroid detection.
They certainly have the potential to do so. And with ongoing research and development, it's only a matter of time before these technologies become an integral part of our toolkit for exploring and understanding asteroids.
This is all so mind-blowing. It feels like we're on the verge of a golden age of asteroid exploration thanks to these amazing technologies. But I'm curious, to bring things back down to Earth for a moment, can we look at a real-world example of how these integrated detection technologies are already being used? The book mentions something called the NEOWISE mission. Does that ring a bell?
Absolutely. NEOWISE, which stands for Near Earth Object Wide Field Infrared Survey Explorer, is a NASA mission that's been incredibly successful in identifying and characterizing thousands of near-Earth asteroids, or NEOs. It's a fantastic example of putting these technologies into action.
So it's like a dedicated asteroid hunter constantly scanning the skies for these near-Earth objects.
Precisely. NEOWISE uses a combination of spectral analysis, thermal imaging, and orbital tracking to create a detailed profile of each asteroid it observes. It's like a cosmic detective agency, gathering all the evidence we need to understand these celestial objects.
That's amazing. And what kind of information is NEOWISE gathering about these asteroids? Is it just about their size and shape, or are we getting deeper insights into their composition as well?
Well, it's a comprehensive approach. NEOWISE is providing valuable data on their size, shape, composition, and even their orbits. Using spectral analysis, for example, NEOWISE can determine whether an asteroid is rich in metals, water, or other valuable resources, helping us prioritize targets for future missions.
So it's not just about finding asteroids, it's about figuring out which ones are worth mining, right? It's like having a cosmic treasure map guiding us to the most promising locations.
Exactly. And the data on their orbits is crucial for long-term monitoring and even planetary defense. By tracking their trajectories, we can assess the risk of any of these asteroids posing a threat to Earth.
So NEOWISE is not just helping us find resources, it's also playing a role in protecting our planet. It's incredible how one mission can have such a multifaceted impact. But speaking of impact, I'm curious about the future of asteroid detection. Will we see even more advanced missions like NEOWISE in the years to come? What are the next big steps in this field?
Oh, the future of asteroid detection is incredibly bright. We're on the cusp of a new era of exploration, driven by technological advancement and a growing understanding of these celestial objects. One exciting development is the potential for deep space probes, equipped with even more advanced hyperspectral cameras and high-powered radar systems, venturing further into the asteroid belt and beyond. These missions could reveal a wealth of new information about the origins of our solar system and the potential resources available to us.
That's a thrilling thought. It's like we're about to embark on a grand cosmic treasure hunt, and these advanced probes are our maps and metal detectors. But it's not just about the technology, is it? It's also about the collaborative spirit of this endeavor.
Absolutely. Expanding international partnerships will be crucial for sharing data, coordinating observations, and pooling resources to maximize our understanding of the asteroid population. It's a global effort to unlock the secrets of the cosmos and harness the potential of these celestial objects for the benefit of all humankind.
So it's like a cosmic symphony, with scientists and engineers from around the world coming together to create a harmonious understanding of these asteroids. And as we gather more data, we can expect to see even greater integration of asteroid detection with other space technologies like those autonomous mining systems we discussed earlier. It's a truly exciting time to be following this field.
It certainly is. The possibilities are vast, and the discoveries we make in the coming years will undoubtedly shape the future of space exploration and our understanding of our place in the universe.
It's incredible to think about the potential impact of all this. But before we get too lost in the future, let's take a step back and explore some more fascinating aspects of asteroid detection. We'll delve into the specific resources we're hoping to find, the ethical considerations surrounding space mining, and the potential role of asteroids in planetary defense. Stay tuned, because there's much more to uncover in this deep dive. We've been talking about the incredible technologies used to detect and analyze asteroids, but I'm curious about the treasure itself. What exactly are we hoping to find on these space rocks? Is it all about precious metals like platinum and gold, or are there other valuable resources out there?
Yeah, it's easy to get caught up in that gold rush mentality when we talk about asteroid mining. But the potential resources are much more diverse and frankly more essential than just precious metals. One of the most valuable resources is water ice.
You mentioned water ice earlier when we were talking about spectroscopy. Why is water so valuable in space? I mean, it's abundant here on Earth.
That abundance is precisely what makes Earth so special. But out in space, water is a precious commodity. It's crucial for life support, obviously, and can be broken down into hydrogen and oxygen, which are incredibly efficient rocket propellants.
Ah, so we're not just talking about drinking water for astronauts. We're talking about creating fuel depots in space, powered by asteroid-derived propellant. That would revolutionize deep space travel.
Exactly. Imagine a future where we don't have to haul all our fuel from Earth. We could set up refueling stations in strategic locations throughout the solar system, making space travel more efficient and cost-effective. That's the, game-changing potential of finding water ice on asteroids.
That opens up a world of possibilities. What other surprising resources might we find on these asteroids? Are there other elements or compounds that would be valuable for space exploration or even back here on Earth?
Absolutely. Some asteroids are rich in carbon-rich compounds, which are the building blocks of life as we know it. These could be incredibly valuable for producing building materials, plastics, and even fertilizers for potential future settlements on other planets or moons.
So it's not just about extracting raw materials, we're talking about potentially creating a closed-loop system where we utilize asteroid resources to create sustainable habitats beyond Earth.
Precisely. It's about becoming a truly spacefaring civilization, not just visitors. Asteroids could provide the resources we need to establish a permanent presence in space.
That's a powerful vision. But I also recall hearing concerns about asteroids posing a threat to Earth. How does asteroid detection play a role in planetary defense?
That's a critical aspect of the field. By accurately tracking the orbits of asteroids, especially those classified as near-Earth objects or NEOs, we can assess the risk of potential collisions.
So it's like having a cosmic neighborhood watch, keeping an eye out for any troublemakers heading our way.
That's a good analogy. And if we detect an asteroid on a trajectory that could intersect with Earth's orbit, we can start planning mitigation strategies, well in advance. The key here is early detection.
When it comes to potential threats, early detection is everything. But what kind of strategies are we talking about? Is it like the Hollywood movies where we nuke the asteroid and save the day at the last second?
Well, while those scenarios make for great entertainment, in reality, blowing up an asteroid could create multiple smaller but still hazardous fragments. It's not the most practical or safe approach. We're exploring more controlled methods, like using gravity tractors or kinetic impactors.
So it's more about nudging a cosmic billiard ball than blasting it to smithereens. A gentler approach with potentially less catastrophic side effects.
Exactly. A gravity tractor would use a spacecraft's gravitational pull to slowly alter the asteroid's trajectory over time. A kinetic impactor would involve a high-speed collision with a spacecraft to, slightly nudge the asteroid off course.
These approaches sound a lot more precise and less likely to turn a single threat into a cosmic shotgun blast.
Precisely. And the earlier we detect a potential threat, the less force is needed to deflect it. That's why continuous monitoring and accurate tracking are so crucial for planetary defense.
It sounds like asteroid detection is playing a vital role in safeguarding our planet's future. It's reassuring to know that scientists are constantly monitoring the skies for potential threats.
Absolutely. It's a testament to the importance of investing in space science and technology, not just for exploration and resource utilization, but also for protecting our home planet. It's about understanding our place in the cosmos and taking responsibility for our own safety.
We've covered a lot of ground here, from the search for valuable resources to the crucial role of planetary defense. It's amazing how asteroid detection connects to so many different aspects of our future. And as we delve deeper into these topics, I keep coming back to the sheer potential of these emerging technologies, especially those quantum technologies you mentioned earlier. Can you elaborate a bit more on how those might revolutionize asteroid detection?
Sure. Quantum technologies operate on the principles of quantum mechanics, which govern the behavior of matter at the atomic and subatomic levels. These technologies are still in their early stages, but they have the potential to unlock a whole new realm of possibilities in various fields, including asteroid detection.
So we're talking about harnessing the power of the very small to help us understand the very large.
Exactly. One promising application is quantum imaging. It leverages the unique properties of entangled photons to create images with, unprecedented sensitivity and resolution. We could potentially resolve surface features on an asteroid that are currently too small or faint to be seen with conventional telescopes.
It would be like switching from a standard definition TV to an ultra-high definition 8K display. We'd see those asteroids in a whole new light, literally.
That's a great way to put it. We could study the detailed geology of asteroids, identify potential landing sites with greater precision, and even search for signs of past or present life with much greater sensitivity.
Wow, the possibilities are truly mind-boggling. And what about quantum spectroscopy? How might that revolutionize our understanding of asteroids?
Well, quantum spectroscopy takes advantage of the incredible sensitivity of quantum systems to detect and analyze light with incredible precision. This could allow us to identify the chemical composition of asteroids with unprecedented accuracy, revealing the presence of rare elements, trace minerals, or even complex organic molecules.
So it's like upgrading from a basic chemical test kit to a state-of-the-art laboratory. able to detect even the faintest traces of elements and compounds.
Precisely. And by studying the subtle variations in the spectral signatures of asteroids, we could gain insights into their formation, evolution, and even the processes that led to the formation of our solar system. It's like piecing together a cosmic puzzle, one quantum measurement at a time.
It sounds like quantum technologies could unlock a treasure trove of information about asteroids and the history of our cosmic neighborhood. It's fascinating to think about what we might discover as these technologies mature.
Indeed. And the research and development in this field are rapidly advancing. It's only a matter of time before these technologies become an integral part of our asteroid detection toolkit, leading to breakthroughs we can only imagine today.
It's incredible to think about how far we've come in our understanding of asteroids, from those early days of ground-based observations to the sophisticated technologies we have today, and the even more mind-blowing potential of quantum technologies on the horizon. It seems like we're on an incredible journey of discovery, uncovering the secrets of these celestial objects and unlocking their potential to shape our future.
It's a journey driven by curiosity, innovation, and a deep desire to understand our place in the universe. And as we continue to explore, we're not only uncovering new knowledge, we're also developing the tools and technologies that will empower us to venture further into space, establish a sustainable presence beyond Earth, and perhaps even discover new forms of life or clues to the origins of our own existence.
Those are big questions and profound possibilities, and it all starts with understanding those seemingly insignificant specks of rock and ice hurtling through space.
Exactly. Asteroids are more than just celestial objects. They're stepping stones to a future where humanity becomes a truly spacefaring civilization, capable of harnessing the resources of the cosmos and expanding our understanding of the universe we inhabit.
It's an inspiring thought, and I'm eager to see what the future holds for asteroid detection and space exploration. But before we get too far ahead of ourselves, let's take a moment to reflect on the journey so far. We've explored the incredible technologies used to detect and analyze asteroids, from radar and spectroscopy to the mind-boggling potential of quantum technologies.
We've also discussed the diverse array of resources we might find on these space rocks, from precious metals and water ice to the building blocks of life itself.
And we've touched upon the crucial role of asteroid detection in planetary defense, safeguarding our planet from potential cosmic threats. It's been a truly insightful deep dive, and I feel like we've only scratched the surface of this fascinating field.
There's always more to explore, more to discover, and more to understand. But as we delve further into the world of asteroid detection, it's important to remember that it's not just about the science and technology. It's about the human spirit of exploration, the drive to push beyond the boundaries of what we know, and the responsibility to use our knowledge wisely for the benefit of all humankind.
That's a powerful sentiment, and it perfectly captures the essence of this deep dive. We've explored the cutting-edge technologies, the scientific discoveries, and the profound implications of asteroid detection for the future of humanity. But before we wrap up, I'd love to get your perspective on one final question. If you could choose one technology to take with you on a mission to an asteroid, which one would it be and why?
That's a fantastic question. It's like asking a chef to choose their favorite ingredient. Each one brings something unique to the table.
Yeah.
But if I had to pick just one technology to take on an asteroid mission, I think I'd go with a hyperspectral imager.
That sounds pretty high tech. What makes it so special?
Well, it's essentially a fusion of spectroscopy and optical imaging,
Yeah.
all in one instrument.
Okay.
Imagine being able to see the asteroid in, stunning detail while simultaneously analyzing its composition at every point on the surface. We could map out the distribution of minerals, metals, water ice, everything.
So it's like having X-ray vision that also tells you what everything is made of? That would be incredible for identifying the most promising areas for resource extraction.
Exactly. And it wouldn't just be about finding the good stuff. We could gain a deep understanding of the asteroid's geological history, how it formed, what it's made of, how those resources are distributed. It would be like reading a biography of the asteroid, written in its own elements.
And you wouldn't even have to dig and take samples to get that level of detail. It's all done remotely with light.
Precisely. Hyperspectral imaging is non-destructive, which is important.
Right.
We want to explore these asteroids sustainably, preserving their scientific value for future generations.
That's a crucial point. It's easy to get caught up in the excitement of resource extraction, but we have a responsibility to approach asteroid exploration with respect and a long-term perspective.
I couldn't agree more. We're not just out there to, grab whatever we can. It's about expanding our understanding of the universe and our place in it.
Yeah. Well, it's been an amazing journey so far, exploring all these facets of asteroid detection. We've gone from basic principles to cutting-edge tech, even touching on the philosophical implications of space exploration.
And we've only just scratched the surface. There's so much more to learn, so much more to discover.
Before we wrap up this deep dive, I want to leave our listener with something to ponder. We've talked about the technologies, the resources, the scientific advancements, but ultimately, it's the human element that drives all of this. What will W or do with the knowledge and resources we gain from asteroids? How will it shape our future as a species?
Those are the big questions, aren't they? Will we use these resources wisely to create a more sustainable future for ourselves here on Earth and beyond? Will we establish thriving settlements on other planets, expanding the reach of humanity across the solar system? Will we unlock the secrets of the universe, perhaps even encountering other forms of life? The choices we make today will determine the answers to those questions.
It's both daunting and incredibly inspiring to think about the possibilities that lie ahead. It's been a privilege to have you as our guide on this deep dive into the world of asteroid detection. Your insights have been invaluable.
The pleasure was all mine. It's always exciting to share the wonders of space exploration with a curious mind. And to our listener, keep looking up at the stars and never stop questioning, exploring, and dreaming. The universe is full of wonders waiting to be discovered.